Hello. Okay. So in this lecture, I'm going to discuss about a sequence detector to detect the sequence of 1001 using Moore overlapping method. Now, in any sequence detector, the toughest thing is to make the state diagram. Means most of the students find problems or difficulties to make the state diagram, what I observed. Now, if you can make the state diagram properly, the rest of the things are very easy. Now in this lecture, I'll basically focus on how to make the state diagram for a sequence detector, which will detect the sequence of 1001. And if you follow the same concept, whatever I will discuss here, then you can implement any other sequence detector using Moore overlapping method. Okay. So the first thing is, as in this problem, the sequence, whatever we need to detect, it is having 4 bits. So the number of states, what you need to consider in this particular problem, that has to be n plus 1, where n is the number of bits given in the sequence detector, number of bits given in the sequence. Okay, so in this problem, the number of bits are 1, 2, 3, 4. 4 bits are there. So how many states you need to consider? 4 plus 1 to 5 states. Okay, and this procedure you need to follow for Moore overlapping method. Okay, so the first thing is how many states you need to consider in the state diagram. That is first state. Now, how to solve this problem? What are the steps you need to follow? That I will tell one by one. So step number 1, as I already told, you need to make the state diagram. And if you can make it properly, then you can think of like you have already solved the 70% of the problem. Rest of the things are very easy only. Okay, now come to this problem. So make this 5 states first. A, then B, then C, D, and E. These are the 5 states. Okay, you need to give this arrow, and whatever the sequence is given, blindly you can write it down here. Okay, 1001. Okay, now after that, what you need to do? That is very important. Okay, so state number A, actually this is known as reset state. Okay, so we'll start from this reset state. Now for each of the state, what are the things you need to consider? Actually, you need to consider two condition of input. Input can be 1, input can be 0. So both the things you need to check, and accordingly you have to decide in which state you need to go. Okay. So suppose for A state, we have already considered the input of 1. What we didn't consider? The input of 0. We didn't consider. Okay. So if the input 0 is given, what you need to do? You need to do the self loop. Why? Because if it is reset state, and if you are starting from this reset state, then that input what you didn't consider, if you consider that one, then in that time you need to use the reset state that you need to remember. Okay, so for state number A, already I have considered 1. What was the input left? Input left was 0. So 0 I have considered here. And as I told, as you are starting from reset state, you have to make the self loop by considering input of 0. Okay, now try to understand this thing. B, what it is detecting actually? B is detecting the value of 1. See, from A to B, you have the value of 1, means B is detecting 1. Now, what about C? What C is detecting? 1, 0. What D is detecting? 1 0 0 1 0 0. Now what E is detecting? 1 0 0 1. You can write it down 1 0 0 1. Okay, I will note this point. This for your understanding purpose only. I told. Okay, and these square boxes also, whatever I have drawn here, this is actually not required for your understanding purpose. I drawn these square boxes because these boxes will be required to make this state diagram. Okay, so step number 1 is state diagram. Okay, so come to B. So for B, what you have already considered? You have already considered 0, input of 0. What you didn't consider? You didn't consider 1. So if you consider input of 1 from B, to which state you need to go, that you need to decide. How to decide? The process is whatever you have written for B in the square box. For B, what you have written? 1 you have written in the square box. That 1 you need to first copy here. Okay. Then after that, for B, what state means, sorry, what input you didn't consider, that you need to write here. So try to understand. For B, what we have already considered, input 0 we have already considered. What we didn't consider till now, input 1 we didn't consider till now. So that one you need to write here. Okay, and that one you need to compare with the square box one. Are they same? Yes. If they same, you need to make the cell blue. If they are not same, you need to go to reset state. So this rule you need to follow. And same thing you need to follow for C also. So for C, every time what you need to do, whatever you have written for that state in the square box. So for C, what you have written in the square box 1 0, that you first copy here. In the left side, you first copy here. Okay. Then the next thing what you need to do, now check for C what input you have already considered 0. What you didn't consider 1. That one you write here. Then take the combination of this right side 2-bit and compare with the 2-bit state. Are they matching? No. If they doesn't match, what you need to do? You need to consider the last bit. Means you need to take 1 bit less. Initially, you have started from 2-bit. Now, as it is not matching with the 2-bit state, you have to take 1 bit, 1 bit less. 1 bit less means if previously it was 2-bit, now you have to consider 1 bit. OK, what is that bit? This right side bit you need to take. So that is 1 only. So as 1 is a single bit, you need to compare with the single bit state. Are they matching? Yes. So you need to make a path from C to B when your input is 1. OK, now come to D. So for D is detecting 1 0 0. What I have written in the square box that you write here. This copy this thing here. And after that, you check for D what you have already considered. 1 you have already considered. What still you didn't consider? You didn't consider 0. So write down that 0 here in the right. OK, and then as it is a 3-bit state, so you just combine this 3-bit. OK. Fine. So now see. First you compare this 3-bit with this 3-bit state. Are they matching? No. If they doesn't match, what you need to do? You need to take 1 bit less. As I already told here also in this stage also I told 1 bit less means you need to consider the right side 2-bit. So 2-bit means you need to compare with the 2-bit state. The 0 0 is it matching with this 1 0 state? No. If it doesn't match, what do you need to do? Now you need to consider single bit. Which single bit you need to take? Now extreme right side bit. OK, so if you can remember from where you have started, we have considered first 3-bit. We have compared with the 3-bit state. It doesn't match. Then we have taken the right side 2-bit. We compared with the 2-bit state. It doesn't match. Now we have 1 bit, and that is the extreme right side bit, that is 0. As it is a single bit, you need to compare with the single bit state. Is it matching? No. Is it matching with the single bit state? No. What is the single bit value? That is 1. And here it is given 0. Are they matching? No. So what do you need to do? You need to come to reset state. So go to reset state. So D2 reset state and your input is 0. Fine. Now for E, you need to follow a different procedure. Okay. So whether it is Moore machine or Millet machine, when you come to the last node of the state diagram or last state of the state diagram, some different rule you need to follow. So in this case, as it is a more overlapping technique, what procedure you need to follow for the last node, what rule you need to follow, that I will tell. Okay. So as I told, for each of the state, you need to consider two input. So if you see here for E, none of the input you have considered. So you first write each of the input. So one of the input can be 0, other input can be 1. Now after that, you have to make a group of these two. You have to make a group of these two. Understood? So if we make this group, then what we are getting? We are getting 1, 1. And if you make these two group, then what we are getting? We are getting the group of this 1 with 0, means 1, 0 we are getting. Okay, so it means we are having a 2-bit value. So 2-bit value means you need to compare with the 2-bit state. Okay. So first compare with the 2-bit state. Okay, so this 1, 1 with 1, 0, are they matching? No. Then what you need to do? You need to take the last bit. What it is? 1. So 1 has to be compared with 1-bit state. Okay. What is the 1-bit state? That is 1. So you check. This one is matching with this one. Yes. So what it means? It means if you consider this one, you have to go to this particular state, that is B only. Okay. So it means you have to go to B from E when the input is 1. Okay. So this part we have completed. Now come for the other combination, that is 1, 0. So 1, 0 is a 2-bit state. You need to compare with the 2-bit state, that is 1, 1, 0. Are they matching? Yes. So it means that from E to C you need to come, because 1, 0 represent this C state. So from E to C you need to come when you have considered the input of 0. Okay. Any other state left in this thing in this diagram? No. So it means that we have got the state diagram. Okay. Now the remaining things are very easy. Okay. So I'll remove this part. This is not required at all. This for your understanding purpose only I have written. You can remove this part. Fine. Now use this state diagram and do the next step. That is, you need to make state table. That is step number 2. What do you need to do? State table. You need to make. Okay. Now how to make the state table? Before that, you need to understand few things. So in the state table, what are the things should be there? You should have present state. You should have input. You should have next state. You should have output. So for the timing, these 4 things are required. Some other things are also required that I will tell in the next step. Okay. So present state is, suppose you have present state of A. Then if the input is 0, then you will go to next step. Some next state you will go. And if you have the input of A, sorry, if you have the present state of A, if you have different input, then you will go to the other state. So it means for each of the present state, you have to consider input of 0, you have to consider input of 1. And same procedure you need to follow for each of the present state. Means you have A, you have B, you have C, and for each of the case, you need to consider two things: input 0, input 1. D, you have E. And each of the case will consider 0, 1, 0, 1, 0, 1, 0, 1. It's very easy to understand. Okay. Now try to complete this table. If your present state is A, if you have the input of 0, where you are going? You are going to the, you are coming back again to the its original state as you have self loop. So if the input is 0, you are coming to original A state. And at that time, what should be the output? Output will be 0. Why output is 0? Because you didn't uh, found out this 1001. Okay, because my required sequence is 1001. So if you come to A state, it is detecting only 0. So that's why you have the output of 0. Now what B is detecting, if you can remember, B was detecting 0. Sorry, B was detecting 1. So what will be its output? 0. Why? Because till now we didn't get 1001 combination. Now what about C? C is detecting 10. This one. So let me use different color. C is detecting 1 and then 0. So it means that it is detecting 10. So what will be its output? 0, because till now we didn't get 1001. We need to get all the 4 bits. Then only you can write output of 1. Okay. Now for D, what we got? 100. Is it our required sequence? Till now not. So we need to write 0. Now come to E. So for E, what is it detecting? 1001. Yes, now this is the sequence what we want. So it means that for E, the output will be 1. Okay, so output generally in case of more machine you need to write, or in case of more representation you need to write inside the circle. Okay, just below this variable you need to write. Okay, now. So complete this thing. So for A, if the input is 0, you have found out. Now if the input is 1, you need to go to B. Okay, see, in case of A, if the input is 1, where you are going to B. So that's why I have written B. And in both the case, the output is 0. Okay. Now do the next thing for B. If the input is 0, for B, if the input is 0, you are going to C. Okay. So for B, if the input is 0, you are going to C. Okay. But for B, if the input is 1, you are making a self loop. If the input is 1, you are making it self. Okay. Now same procedure you have to follow. For C, if the input is 0, you are going to D. Okay. If the input is 1, you are going to B. Likewise, for D, if the input is 0, you are going to A. If the input is 1, you are going to E. Now from E, if the input is 0, you are going to see this picture. If the input is 0, you are going to C. And if the input is 1, you are going to B. Okay. And now write down the output. Only in the last case you will have the output of 1. Now you have to remember one thing. In case of Moore machine, when you write, you have to write 1. Actually, if you are traveling from a state where the output is 1, then in that case only you have to write 1. See, when you are moving from E to some other state, try to understand what I'm saying. Note it down this point. When you are moving from E to other state, then only you have to write 1. Okay. And you should not write 1 if you are going to E from other state. If you are going to E, in that case, you no need to write 1. From E, if you are going to other state, then only you have to write 1, because below E only this output 1 is written. Okay. So it means when you are traveling from that node to other node, that time only this 1 will come. And if you are traveling from other node to that node, that time this 1 will not come in the output. So you need to remember, if you are traveling from that node, then only you need to write 1, not to that node case. From that node case only you need to write 1. Okay. Okay. Now the next thing. Now what you need to do? Again, you need to modify the state table using some values of these different states. Now in this particular problem, how many states you got? 1, 2, 3, 4, 5. 5 different states you got, A, B, C, D, E. So each of the state has to be represented by the combination of some binary values. So how many bits are required? That is the important thing. At least you need to have 3 bits. Why 3 bits? Because as you have 5 different states, each of the state has to be represented by at least 3 bits, because if you have 5 different combination, at least you need to have 3 bits to represent each of the combination. So that's why each of the variable has to be represented by 3 bits combination. So A will be represented by 000, B is 001, C is 010, D is 011, and U will be represented by 100. Understood? The thing is, why we didn't consider 2-bit? Because if we consider 2-bit, then we can get maximum 4 combination. 4 combination means 4 states maximum we can get. However, in this problem, we have 5 states. So we need to have at least 3-bit to represent each of the state. Okay. Now replace each of the variable values by this bit combination. Here A, whenever A will be there, where means in the positions wherever A will be there, we need to replace it by 000. If B is there, we need to replace by 001. If B is there, we need to replace by 001. So in this table, wherever A, B, C, D, E are there, you need to replace by these values. This is the ultimate meaning of this thing. Okay. So I am rewriting this table again. So present state you have, then you have input, you have next state, you have output, and something also you need to do. So present state, I can write this values Q2, Q1, Q0 as 3 bits are there. Input, I will use X to represent input. So for next state, I can write Q2 plus, Q1 plus, Q0 plus, and output I can use Z variable to represent that thing. Fine. Now what I need to do? I have to find out I need to replace the variable by these values. Okay. So 000, as you have A, you have considered 0, you have considered 1 as input, and then you have B 001, 001, 01. Then you have C, that is 010, 010. Then you have D 011, 011. Then you have E 100, 100. Okay, so if you just see this table, if the present state is A, input is 0, the next state is A. A means you need to replace this A by 000. Then next one is B. B means you need to replace it by 001. And the next one is C. C means it has to be replaced by 010. Then what you have? You have B. B means it has to be replaced by 011. So likewise, you replace all the ones 011, 001, 000. Then you have 100, 010, 001. Oh, another thing I forgot to write. Yeah, I written actually. This step 2 at V, we're making the state table. Yes, I have written. Okay, now we can write the output also 000000000, and here it is 11. Okay, now suppose we are using JK flip-flop to implement this circuit. Okay, so how many JK flip-flops will be required? Definitely, it should be 3 JK flip-flops. Why? Because 3 bits are there. As each of the flip-flop can store 1 bit. So to store 3 bit, you need to have 3 flip-flops. So what are the flip-flops? J2, K2. These are the inputs of the flip-flop number JK flip-flop 2. Then we have J1, K1 for JK flip-flop number 1. Then we have J0, K0 for JK flip-flop number 0. So 3 JK flip-flops should be there. Now how to identify their values? The thing is you need to use the excitation table. If you can remember, what is the excitation table of JK flip-flop? Suppose if you have the present state of Q and the next state of Q plus, and if you have J and K, what should be the JK value based on the excitation, based on the different combination of present state and next. Suppose this present state, this next state. Okay, so 0, 0, 0x, 0, 1, 1x, 1, 0, x1, 1, 1, x0. This should be the value of J and K. Okay, according to this excitation table. Excitation table of what? JK flip-flop. So we need to use the excitation table of JK flip-flop to determine the value of this J2, K2, J1, K1, and J0, K0. How? If it is 0, 0, then you need to write 0x to follow 0, 0, 0x, 0, 0, 0x. See here we are comparing Q2 and Q2 plus. So we need to write the values for J2 and K2 as we are considering second flip-flop value. Okay, so write down and 0, 0, 0x. So follow the same procedure for each of the combination. Then it will be 0x, 0x, then 0x, then 1x, then x1, x1. Okay. Now follow the same procedure for the next bit, that is Q1 and Q1 plus. So now we are considering flip-flop number 1. So you need to find out the value of J1 and K1. 0, 0 means 0x, then 0, 0, 0x, 0, 1, 1x. So likewise, write down all the values. Okay, so this I have written according to the excitation table. Now do the same procedure for bit number 3, that is Q0, Q0 plus. So you have 0, 0, 0x, then 0, 1, 1x. So like that only for each of the combination, you need to follow the same procedure. So x1, x0, then 1x, 1x, x1, x1, 0x, 1x. Okay. Now, after that, what we need to do? So these all values we need to find out. Z, J2, K2, J1, K1, J0, K0. All these 7 variable values we need to find out. Okay. So how to do? Using KMF only. So 7 KMF we need to do. So this is a lengthy procedure, but the things are very simple. So 7 KMF we need to make. So I'll show one of the KMF. Remaining thing you can do it to find out the values for the other variables. So I'll show for J2. Okay. So the thing is, when you are making this KMF, how many input variables you need to consider? That is the most important thing. So for this problem, how many input variables are there? You have Q2, Q1, Q0 and input X. 4 variables are there. Q2, Q1, Q0 and input variable X. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1. Oh, sorry. 1, 1, 1, 0. Now I'll do for, suppose I'll do for K2 or J2. I'll do for J2. I follow the same procedure for the other variables. So we have 0, 0, 0, 0, 0, 0, 0, 7 zeros are there. 1, 2, 3, 4, 5, 6, 7 consecutive zeros. 0, 0, 0, 0, 0, 0, 0. These are the 7 consecutive zeros. Fine. Then we have 1, don't care if I'm not wrong. We have 1, don't care. Okay. Then we have 1, don't care. How I am putting the values in the KMF, that is according to the whatever position is there, according to that position only I'm putting the values. Okay, so you should know how to put the values in the KMF. Okay, so I'm considering you know how to put the values. Okay, now these remaining values are not present means you need to consider by default don't care. Now we can make a pair between these two. So what should be the expression for J2? From the left side it is Q1, from the top it is Q0X. Okay. Now same procedure if you follow for K2. Now for K2 X, 1, 1. So it means that all the positions are occupied either by don't care or 1. So what does it mean? By default it will be by default blindly we can write K2 equal to 1 because all the positions are occupied by don't care or 1. Means no 0 is present in the table for K2 C column wise, no 0 is present for K2. So by default, it will be 1 only. Okay. So follow the same procedure for the other variables also. You put the values in the KMF and get the values. So you need to do this thing for Z, for J1, K1, J0, K0. 7 different KMFs you need to make. So 2 cases I shown. Remaining thing, if you follow, then what values you will get directly. I'm writing it here. So J2 I have already written. What should be K2? I have already written. J1 value will be Q2 x bar plus Q0 x bar, and K1 will be x plus Q0, and J0 will be x plus Q1, and K0 will be x bar plus Q1, and Z will be Q2. So these are the values we are going to get from this different 7 KMMs. Okay, you can try this part. Okay, now after that, how to make this circuit, sequence detector circuit. So you know, as you have 3 flip-flops, so you have to draw these 3 flip-flops first. Okay, flip-flops are J to K2, and you have output of Q to Q2 bar, and you have J1 K1, output of Q1 Q1 bar. Then you have J0 K0, Q0 bar, and Q1 sorry, it's not bar. Q0, and here it should be bar. Okay, now see for J2, what was the expression? Q1 Q0 into X. So ideally I should take the connection from this Q1 and this Q0 and some input X. But if I take so many connections, as 7 different variables are there, so many connections will be there. So it will be confusing. So what I am doing separately, I am writing the values so that the circuit will look clear, so that anyone can understand. Okay, so in this AND gate, what should be the input? Q1, Q0, and X. That is J2. So I am giving this the output of this AND gate as the input of your J2. Then K2 is logic 1. Then you have J0 equal to no, J1. J1 equal to Q2 X bar. So it means I need to take some AND gate OR gate combination. First of all, I need to take 2 AND gates. This is one of the AND gate. This is the other one. The inputs are Q2, then X bar, and in the other case that is Q0 and X bar. These are the expressions that we got. Okay, then we need to use one OR gate. The OR gate input has to be, or the output of the OR gate has to be given to the input of J1. Now, what about K1? K1 is X plus Q0. So Q1 is X plus Q0 means you have to use one OR gate. X and Q0. Now, what about J0? J0 is X plus Q1. So you can make one OR gate. X plus Q1. What about K0? X plus, no, not X plus, X bar plus, I think. J, which one we are doing? J. J is X plus Q1. Okay, not bar. X plus Q1. This case means in the second K0 is X bar Q1. So this K0 is X bar Q1 means we need to use one OR gate. X bar Q1. Right? And what about Z? Z is nothing but you need to, Z is your output that you need to take from Q2. Okay. So this procedure you need to follow, and one more thing. You have to give clock to each of the flip-flop. That is the most important thing. Each of the flip-flop has to be given a clock. And they should work simultaneously. Okay, so these are the steps you need to follow to make this 1001 sequence detector using Moore overlapping method. And this is not only for 1001. If you use 1011 or 1100 or different combinations also, you can follow these steps to do this sequence detector. Okay, thank you.